Christian. So like you said, I'm Justin Williams. I'm working somewhere in between our high energy physics group and our nuclear physics group here at KU. I know most of you, maybe some of the newer students, I haven't gotten the chance to meet yet, but hopefully I'll get to meet you either this semester or sometime next semester. So today I'm going to talk about how the research that I'm doing here is shining light on the mysteries of the universe. And there's a pun in that title somewhere. Maybe you'll pick up on it later. But I know that we haven't had a colloquium speaker this semester from the LHC, so I'll spend the first part of this talk kind of introducing particle physics and talking about what it is we do at the LHC before diving a little bit deeper into the specific research project that I'm working on. So I want to start out talking about why do we do particle physics? Since the beginning of our existence, humans have looked out into nature and wondered how the world works. What makes up the stuff around us and how do these things work together? Physicist Brian Greene famously says that this is what separates us from other species of animals, is our curiosity, our desire to understand the world around us. And as scientists, typically when we want to understand things, we like to classify. And so a familiar example from chemistry is the periodic table, right? So the periodic table tells us about the individual properties of all of these elements, as well as what happens when they come into contact with one another. And we have something similar in particle physics, but on a much, much smaller scale. So we have the Standard Model. So the 17 particles shown here are the fundamental constituents of all known matter in the universe. The Standard Model tells us about the individual properties of these particles and how they interact with one another. And the Standard Model has done such a good job of describing all experiments that we've done here on Earth that it's been called the most successful theory in the history of the world. So the Standard Model can also be expressed as an equation written in the form of a Lagrangian. And it's so compact that it fits on a coffee mug or a t-shirt or an umbrella or really anything else that we can sell. But even though the Standard Model has been so successful, there are still some shortcomings. And the best way I've heard this said is that it's not broke, but it needs fixing. So let me tell you a few of the problems with the Standard Model. One issue is that it describes 3 out of the 4 forces in nature. So it describes the electromagnetic force, the strong force, and the weak force, but it doesn't say anything about gravity. Also, we know that there are these things in our universe that we call dark matter and dark energy, and we see their effects out in space, but the Standard Model doesn't tell us anything about these either. And then finally, at the beginning of the universe, we know that matter and antimatter should have been created in equal amounts. But today in the observable universe, we see much more matter than antimatter. And the Standard Model doesn't give us a reason for that. So these are the glaring issues facing the Standard Model. This is what keeps particle physicists engaged. And this is what keeps particle physicists in business. But how can we find answers to these questions? Well, ideally, we would jump into a time machine and go back to the early universe and see how all of this matter came into existence. At the time of the early universe, we know that there was an extremely high energy density. This is because all of the energy in the universe, all of the matter in the universe, was contained in a very, very small space before space began to expand into how we know it today. And what's interesting is that we can actually recreate this energy density here on Earth using particle accelerators. This is how it works. When we accelerate particles to the speed of light and smash them together into the tiniest possible space, that energy density at the point of the collision actually corresponds to the early universe about a nanosecond after the Big Bang. This is why we spend billions of dollars to build these facilities to answer questions about our universe. So I'll tell you a little bit about the facility that I'm using, that our research groups here at KU are using to study these types of physics. So we're using the LHC, and you may have heard one of your professors mentioned this in a class. Maybe you read an article on Facebook, or maybe you're doing physics analysis at the LHC. But I'll give you a little bit of details about it because I'm sure you'll hear more during your time at KU. So the LHC is a 27-kilometer ring that's located underground near the city of Geneva, Switzerland, and accelerates particles, mainly protons, to the speed of light, where they collide at various points around this ring. And these collisions aren't just taking place, once or twice a day. They're actually taking place more like 1 billion times per second. A fun fact that I like to tell people about the LHC is that the magnets we use to accelerate the protons need to be cooled to a temperature colder than outer space. But the temperature at the very point of the interactions is 100,000 times hotter than the sun. So that makes the LHC both the coldest and the hottest place in our solar system. Now, one of the points where protons collide around this ring is inside of the CMS detector. CMS stands for compact muon solenoid, and this is the detector that I'm using and our group is using to do physics research. So this is a general purpose detector that's made for measuring all of the particles that come flying out of these collisions. Maybe the most important feature of this detector and how it gets its name is this really powerful solenoid that's built into the detector. It generates a 4 Tesla magnetic field that's useful for bending the trajectory of charged particles. This allows us to infer how much charge a particle has and helps us to identify what type of particle it is. So CMS is a cylindrical detector. And it's actually made up of many layers from the inside out. I think this figure does a good job of showing you those layers. Also gives you a feel for the size of the detector with respect to a person. And here is yet another figure of CMS, but this time we're looking at a transverse slice of the detector as if we're looking at it head on. And I think this is the best figure for seeing the different subdetectors that make up CMS. So starting from the innermost layer, we have the tracking layer, which is able to measure the trajectory of particles as they fly through this portion of the detector. And our HEP group here at CMS is heavily involved with the development of the tracking layer. Just outside of that is the electromagnetic calorimeter. And this is specifically designed for measuring photons and electrons. So photons and electrons will travel from the collision point until they reach the ECAL, the electromagnetic calorimeter, where they deposit their energy here. Just outside of that is the hadronic calorimeter, used for measuring hadrons such as pions and kaons. So those types of particles will deposit their energy here without traveling any further. Outside of that is the solenoid that we mentioned, and then the outermost layer is the muon chambers, obviously for detecting muons. And so when you put all of this together, a typical collision that you might see with the CMS detector may look something like this, where the blue outline is the outline of the cylindrical CMS barrel. And then you see various particles coming out of this collision. So there's an electron here in green going into the ECAL, a couple of muons here in red going into the muon chambers, and then some sprays of hadronic energy in the forward regions we call jets. But this isn't the information that we get from the detector. It's actually a lot more basic than that. Actually, really our starting point is simply just energy readouts from the detector. So it actually may be more like this, where we know some energy was deposited here, more energy was deposited here, so forth and so on. And then we rely on complex algorithms to reconstruct actually what types of particles cause these detector readouts. So in CMS, we use a reconstruction method called particle flow, and it's unique in that it considers the entire event before making any inferences about what types of particles were present. So when we apply this reconstruction algorithm, our output, or what we actually need for physics analysis, are the classification or the type of particle. We need its momentum and the path it took through the detector. And that's what this reconstruction gives us. Now, this reconstruction isn't a one-person job, right? The development and the improvements of this algorithm really take a whole team effort. Unfortunately, CMS, or the people working on the CMS experiment, is one of the largest collaborations in the world. So this collaboration consists of over 4,000 particle physicists, engineers, and computer scientists from 229 institutes from 52 different countries. It's my opinion, after working with this collaboration for 4.5 years, that CMS is really the epitome of teamwork. I mean, it takes a lot of emails, a lot of Zoom meetings, and a lot of coffee to get work done in CMS. And it's been really cool to see what you can do when you bring 4,000 of the world's smartest people together working towards a common goal. Another reason it's so important that we have such a large collaboration is because there's so much data at the LHC that needs to be analyzed. So to give you a feel for how much data we have, we said that these collisions at the LHC are taking place about 1 billion times per second. And we do this over the course of years. So obviously we can't store information from all of those collisions, but even though we only keep about 0.01% of that data, it's still more data than is generated by all the social media websites in the world combined. And so when we're doing these various physics studies, when we're trying to answer these questions facing the standard model, the tricky part is that our answers to these questions may appear in the form of very rare events or very rare collisions. So over a year's worth of data taking, you may be looking for only, let's say, 5 or 10 of these collisions. So in essence, it's like searching for a needle in the world's largest haystack. So when we're doing these studies, obviously we can't go through one by one and look at these collisions with just our eye, right? That would take forever, longer than any graduate student has. So we need to use the computing capacity that's available to us today in order to sift through all of this data, this massive haystack, to look for the collisions that we actually care about, the collisions or the events that will give us clues to how the universe works. And so to do this, we use various software packages. Here in CMS, our largest one and the most important one is called CMS software, or CMSSW. And some of your peers, other graduate students in our group could attest to this, but this is the reoccurring nightmare of every graduate student. I mean, this is a massive software package that's been compiled by many people over many years. So this GitHub screenshot is just to show you that it has over 200,000 commits and over 800 contributors. It's made up of many different languages, and just overall, it's just very complex. The worst part is there's no user's manual for this, right? People would tell you that really the user's manual is just to simply start using it, right? That's the best way to figure it out. So after struggling with this for many years and being able to use it, I've actually gotten to the point where I'm one of these, 900 contributors. So that has been a journey. And then so to actually use this software package, to actually look through this data, this isn't something that can just be run on a simple laptop, right? It can't be run locally. But we use a worldwide computing grid in order to have the power to process all of this data. So it's really cool to think about that when I start some data processing and I go to bed at night, some of this data is being processed in India, some of it's in Europe, maybe some of it's in California. But it's really cool, and ultimately it's the only way that we can do physics analysis, by having this power of a worldwide computing grid. Okay, so up to this point, I've talked very generally about particle physics and doing physics analysis at the LHC. But now I want to move a little bit more specifically into what it is that I do. So we said that the LHC is a proton-proton collider, and typically that's how it's used. So in a typical collision at the LHC, two protons smash together and are completely destroyed. And in the process, they create some other particles that we measure in our detector. However, there's a unique opportunity to use the LHC as a photon-photon collider. Photons being the particles of light, and that's where the pun comes from in the title. So let me tell you how this works. As these protons are accelerating around the LHC, they emit electromagnetic fields, right? Because moving or accelerating charged particles have this property. Now, the equivalent photon approximation tells us that these E and M fields can be equally viewed as a flux of virtual photons. That means that when two protons pass just near each other without actually smashing together, there's a chance to observe these photon-photon collisions. Now, when we have these photon interactions, there's a number of different results that we could have. The specific result, or the specific process that I'm interested in studying, is shown here in this diagram. If you haven't seen a diagram like this before, it's called a Feynman diagram. And a lot of people think it's a spatial representation of a process, but it's actually a time representation. So as we move from left to right across this figure, we're actually moving forward in time. So what this diagram is telling us is that there are two incoming protons. These are the protons being accelerated around the LHC. Each of these protons emit a photon where they interact at this shaded circle to produce two new or different photons in the final state. Additionally, our original protons remain intact in the final state. So we have four final state particles. We have two photons being produced, and we have our two original protons. And so this process of two photons producing two new photons is called light by light scattering. And since this process happens by photon interactions, it's governed by the theory of quantum electrodynamics, which is a theory of great precision. So we know the production rate, or the cross-section, of this process extremely well. It's predicted by the standard model. And this process, this light by light scattering process, has been measured by both the CMS and ATLAS collaborations. Here's actually a picture from the ATLAS press release showing the two photons in their detector. However, I'm not interested in studying this process for its standard model implications. I'm actually interested in it because there are many theories beyond the standard model that predict enhancements to the production rate, or the cross-section for this process. So these theories are theories of dark matter, extra dimensions, gravitons, things of this nature. And so since we know the cross-section so well, we can look for any enhancements to the cross-section that could be signs of new physics, or physics beyond the standard model. So in order to study this process of these four final state particles that we can measure, we need to use a system of detectors. So the CMS detector you're already familiar with, but additionally, we need to use a set of forward detectors located about 200 meters on either side of CMS. So this diagram is showing you just one side of these detectors, but a symmetric set exists on the other side as well. These set of detectors are known as the Precision Proton Spectrometer, or PPS, and they are specifically designed to measure protons that undergo an interaction in CMS, but remain intact and continue to travel down the beamline. Then based on their horizontal displacement from the beamline, we can infer how much momentum was transferred during their interaction inside of CMS. So later we'll see that by measuring the momentum of these protons, we get a very powerful tool for analysis. But I will talk more about that in a few slides. So just to reiterate, we have these 4 final state particles, right? So we're measuring these 2 photons inside of the CMS detector, and then the 2 protons are measured on either side of CMS in these forward detectors called PPS. So for a second, I want to focus just on these 2 photons, or I'll call them the diphoton system, because there are many ways that 2 photons could be produced inside of CMS, but we want to make sure that the photons that we're looking at are truly coming from this light-by-light scattering process. So what we can do is we can use simulations of this process to see how we expect these photons to look in our detector. So here on this slide, I'm showing you that simulation of the light-by-light scattering process in the form of 2 histograms. Histograms are a really powerful tool in particle physics because usually we want to study numbers of events. So that's why they're so useful. So these 2 histograms are as functions of 2 variables describing this diphoton system. On the left, we have the diphoton mass, and on the right, we have a variable that represents the angle separation between the 2 photons. So this variable is called the acoplanarity. And what you'll notice from looking at these 2 histograms is that our signal events, this light-by-light scattering signal, appears at high values of the diphoton mass and appears at low values of acoplanarity. So we can use this knowledge of the light-by-light scattering process, as well as other knowledge that I'm not showing you here in this slide necessarily, to develop a selection criteria that will be useful for selecting events that are consistent with the types of events that we expect to see from light-by-light scattering. So this criteria is meant to be an illustration of the selection criteria I'm using in my research, but it's not an exhaustive list by any means. There are some more criteria that are a bit too technical. But the idea of this is that there is a list, basically a checklist that a collision needs to pass. And if it passes that, that entire checklist, then we can say, okay, it has properties that are consistent with what we expect from these light-by-light scattering processes. So this checklist consists of having 2 particles in CMS that have been reconstructed as photons. And then on top of that, we apply an even more rigorous criteria to truly verify that these 2 particles are in fact photons. And there's also a veto to veto particles that are electrons, because in the electromagnetic calorimeter, photons and electrons look really similar. Then we use our knowledge that we saw from simulation on the last slide to select events that have high diphoton mass values, so above 350 gigaelectron volts. And then in the same way, we want to select events that have very low acoplanarity, because we saw that that's what we expect in our simulation. And then finally, we can make this, this last selection basically to select events that have a momentum values of the photons, where we expect that the protons leading to this event could be detected in our forward detectors. So this checklist, or this selection criteria, is meant for selecting our signal. And so I'll refer to this as our signal region. But even though we've made this checklist, we've made this signal region to be inclusive of our light-by-light scattering signal, we still expect it to be dominated by other standard model processes. So to make sure that we fully understand this signal region, we can study it with simulations of those various standard model processes. So again, this is another histogram, and you'll see histograms on more of the following slides as well. And again, this is as a function of the diphoton mass. So what you see here in these black points are data from the LHC, so numbers of events from data. And then the colored histograms are various standard model processes. And so since we expect this region to be dominated by other standard model processes at the LHC, we expect that the sum of these colored histograms should be equal to the number of events in data. And that's what you see here. There's pretty good agreement between the black data points and the sum of the histograms. And you can see that further in the ratio plot here below, where the number of events in data divided by the number of events from the simulation falls along the line y = 1 within uncertainties. We don't just do this for one kinematic variable, the diphoton mass. To be sure that we understand this region, we want to study many different variables. And so here's just a small subset just to illustrate that there are many variables that we want to check for this good agreement. So now I want to go one step further. So before we were just considering all types of processes that would create 2 photons inside of CMS. Now I want to be a bit more specific and consider events that would create 2 photons in CMS and 2 protons in the forward detectors. So again, we'll look at a histogram as a function of the diphoton mass. And this is all a simulation. So this black line is a simulation of our light by light scattering signal here in the black line. And then again, the colored histograms are simulations of various standard model processes. And so there is a big conclusion that we can take away from this plot, this histogram. And it's that at increasingly high values of diphoton mass, there's only one of these colored histograms that is as significant as our signal shown in black. And it's this red histogram, which corresponds to pileup. And I'll tell you a bit about what that is. So pileup at the LHC stems from the fact that the LHC doesn't just collide one proton at a time. It overlaps packets of millions of protons at a time, and every crossing of these packets, we expect about 40 to 60 protons to collide. And so that creates a mess inside of the detector that looks something like this, even though this is only about 20 different collisions. And so what can happen when you have this giant mess in your detector is that there can be overlapping events that may look like our signal, even though they're not. And I'll explain how that works. So you can see in this diagram, you could have one collision that produces 2 photons inside of CMS, but both of the protons are completely destroyed. And that could overlap with one or more events that don't create any photons in CMS, but leave one or more protons intact in the final state. And so this overlapping of collisions would look like our signal, would fake our signal, even though it's obviously not. And we refer to those types of events as background events. So I alluded to earlier that since we are measuring the momentum of all of our final state particles, it'll give us a very powerful tool for our analysis. And this is how it works. Since we know the momentum of our original 2 protons, and we know the momentum of all of our final state particles, we can apply a conservation of momentum to these systems. And the way that we do that is by basically applying a conservation of momentum between the central diphoton system and the forward proton system. And it's been shown that when we apply this conservation of momentum, we can reject basically all of this background that comes from pileup. So when we apply this conservation of momentum, we apply it by looking at two variables, right? The two variables that make up momentum, mass and velocity. But in particle physics, we use a relativistic velocity that we call rapidity and denoted with a lowercase y. So when we want to apply this conservation of momentum or match the variables between these two systems, we can do that using these two plots shown here. And it's worth noting that these are no longer histograms. These are simple scatter plots, right? So the variables for mass are on this left plot, and the rapidity matching, or the variables for rapidity, are on this right plot. The variables for the two proton system are on the x-axis, and the variables for the diphoton systems are on the y-axis. So how this would appear if there was truly an event that had this conservation of momentum, a true signal event, it would fall along the y equals x line in both of these plots, right? So if there was an event that had a matching between the mass variables, it would be here. An event matching in rapidity would be here. And so when using all of the data collected in 2016 with these detectors, we see that there is one event matching in rapidity and no events that match in mass. So therefore, we conclude that with this amount of data, we see no events that are consistent with the light by light scattering signal, and no events for evidence beyond the standard model. So the analysis isn't over at this stage, right? We need some conclusion. And so what we do in particle physics, when we see nothing, see no events that are consistent with new physics, we communicate that to the community by placing limits. And so here you can see the limits that we placed on two parameters that govern this 4-photon coupling, zeta 1 and zeta 2. Yeah, you can see those here. So this study has been detailed in a really extensive analysis note that's about 120 pages that is for internal CMS use. And then all of that information has been condensed into about 5 pages for a public document that you can find here at this link. So for the rest of my time in graduate school, my task is to redo that entire study, but with about 10 times as much data. So data from 2016, 2017, and 2018 at the LHC. And I'm happy to be able to say that most of that work is already done. There's already one of these extensive analysis notes written for this study. In addition to just redoing the study, I've actually added many improvements. So just to list them quickly, there's a more robust treatment for our systematic uncertainties. I've developed a completely data-driven background estimation approach. And we're also using a new photon identification criteria, just to list a few. Okay, so I will wrap up. So to answer my earlier question, the reason we do particle physics is because it gives us an opportunity to better understand the universe. And the LHC has done its part in that by providing over 100 million terabytes of data for us to analyze. And during my time at KU, I've gotten to analyze that data through the lens of photon interactions as a way to search for new physics. So thanks for being here. Thank you for your attention, and I can answer any questions.
Thank you very much, Justin, for a very interesting talk, and really on a pioneering type of analysis now at the Large Hadron Collider. If there are questions, feel free to raise the hand. I'm looking at the participant list. If there are any questions from the audience. Oh, sorry. Yeah, I just saw Muhammad Ful Hussein. Yes, feel free.
Yeah, I have a couple of questions. So why don't the muons end up getting detected in the electromagnetic calorimeter in CMS?
Yes, so muons are harder to detect than most particles. That's why they need these dedicated, really dense muon chambers. And so the idea is that all of these uh, all of these subdetectors are made with specific purposes. So the specific material that's used in each of these is made to detect certain types of particles. So the material that we use in the ecal doesn't interact with muons as they travel through, which is why they're able to travel through all of this and the HCal as well. But the muon chambers are designed specifically to interact with muons most of the time.
But muons are they can be interacting with by electromagnetic interaction, right? So in the way they will face like thousands and thousands of electrons, like electrons do. If one GeV muon is traveling, it can lose half of its energy in uh, by like muon plus a photon 500 MeV, and then that photon can like give rise to muon and anti-muon like the electron does, right? In the same way.
So you're saying if a muon, turns into another type of particle, is that what you're saying, or am I misunderstanding you?
No, like electrons lose their energy in the
Mhm.
electromagnetic calorimeter in the way that they goes and they give half of their energy to a photon, and it goes away, right? Like in Brahmstroom, like
So
electron comes and give half of its energy to a photon, and it goes away.
so I'm not sure that I understand the second part of your question, but uh, Chris or Jack, what's the material that the ecal is made of? I don't want to confuse it with Atlas.
It's made of lead tungstate crystals.
Lead tungstate crystals. So these lead tungstate crystals um, are specifically designed to uh, to measure to have electrons and photons interact with them, but not muons, right? Whereas, and I don't know what the muon chambers are made of. Oh, iron yoke, here it is. But this iron yoke is able to detect muons. So that's the part of your question I do understand. If there's another part that I'm not answering, then I apologize.
No problem. So why is the curvature of the muon track changing? Like,
Oh, the curvature of the track is changing because of the solenoid, right? Because these charged particles bend throughout the detector. So that's why. So this red track is for an electron that's deposited in the ecal, but the photon doesn't bend, right? Because it's not a charged particle. So that's why the muon does take this weird trajectory.
no, is this track specific for a like mu plus anti-muon? Is this because it should have the similar curvature as electron, right? If it is mu minus.
Right. Wait, you're saying that it should curve this way instead of
Yeah,
that way?
right. If it
Yeah.
is mu minus, then so it is mu plus basically.
Yeah. So yeah, I didn't make this figure.
Okay,
But
okay,
yeah.
okay. I thought you made it. Anyway,
Yeah.
I have one more question. In the
Yes.
light by light scattering, you
Uh,
showed what happens in the shaded part of the Feynman diagram.
Yeah, good question. So there is a number of different things that could happen there. This could be your exchange. Well, so in the standard model, I should say, this could be a box of quarks uh, or W plus or W minus bosons, right? In a loop here. And then in BSM theories, this could be an exchange of a dark matter particle or an axion-like particle via some like S-channel exchange here. So there's a couple of different ways it could happen. It's different in the standard model than in BSM theories.
I see. So like when you are saying diphoton mass,
Mm-hmm.
which two photons did you mean in this
Yeah,
figure?
so it's for these final state photons because
So
we
they
can't,
they are
yeah, we
they
can't
are
measure.
like they're like real photons, right? So how can they have mass? Like they should be massless.
So in CMS, we define mass basically as a function of PT and eta. So the photons have some transverse momentum, and we use their eta value to calculate what we call the diphoton mass. So these two photons by themselves are massless, but the system of particles we calculate a diphoton mass for that's just based on their transverse momentum and their eta values in the detector.
Okay.
Chris, were you trying to say something earlier? Did I cut you off?
No, not at all.
Oh, I thought somebody else was saying something.
Thank you.
Yeah. Thanks all for the question. I see Jack has his hand up, and then Dave. So Jack, feel free.
Okay, and excuse me my knowledge of Greek letters. I believe in the eta is eta this fancy E parameter that you're using to determine whether or not the probability of the proton is seen in the PPS detector.
Oh, sorry. It's actually Xi.
Okay. Yes, exactly. You got it. Like I say, I didn't get the name, but you didn't go into much detail about what this parameter was. I was wondering if it'd be possible to briefly discuss what this is.
Yeah, sorry. I didn't want to be too technical, but it's a good question. So when we measure protons in this forward proton detectors, typically the variable of interest is Xi, which is the fractional momentum loss. And then so in CMS, when we have these two photons, we can derive an equivalent Xi variable for the diphoton system. And so that's really useful because you basically have these two systems basically in the same language in terms of Xi. So for the protons, it's basically the fractional momentum loss. And here, basically the physical meaning would be the momentum that's transferred to the diphoton system.
Okay.
Thanks. Yeah, it's like X Bjorken, but for the photons, basically.
Mhm.
Dave, feel free to ask a question or to comment.
Sorry, is that me, Dave?
Yes, sorry, yeah, Dave Bassett.
Yeah, sorry, yeah. Yeah, thanks very much, Justin. That was really very well presented. And I'll mention my kids are very excited to know that you're presenting here today. I did have so I never understood light by light scattering. I could never get past the idea that the photon is uncharged, but it still is interacting. And as I understand it now, it's because of essentially some sort of vacuum polarization loop that is producing some virtual particles, and that's what's interacting. Is that correct?
Yes, that's correct. I think it might, it's kind of shown here in this. Yeah, so there would basically be a box of these, these fluctuated particles. So whether it's a quark, lepton, or W boson, and most likely a W boson, that would be in this loop that could give rise to these two photons.
Okay, so that helps me understand a lot. I just had a very dumb question, which I should remember from when I was in grad school during the Civil War. That virtual loop, I would have thought heavier particles are suppressed inside that virtual loop because maybe they're not. Maybe the energy of the photons is so high that there isn't a big mass suppression for W plus particle energies versus electrons. Is that right? So you're still sensitive to very heavy objects.
Yeah, exactly.
Okay.
Yeah, and so actually that actually presents a really good point that I avoided. But so when Atlas and CMS originally studied this process, it was in lead-lead collisions. So that's really useful because you get a higher photon flux, but you get smaller photon energies. So you do kind of miss out on maybe heavier objects that could contribute to this process. But the advantage of us studying proton-proton collisions is that we get higher photon energies and could be sensitive to different types of different types of particles that could give rise to these diphoton events.
Okay, got it. Yeah, thanks very much. That was quite nice.
Thanks.
Betsy, I see you have your hand up, so feel free to comment or ask a question.
Yeah, I mean, first of all, thank you so much, Justin. It was a really lovely talk, and I found it incredibly accessible. So really nice background, especially. I was curious, to what extent is CERN and CMS, to what extent are these like the optimal facilities to do this study? I mean, you have this really nice result, and I'm curious, would there be any changes in facilities or detectors that would sort of better enable doing this study, right, and getting more sensitive results?
Yeah, so the advantage of this study is that we have all of the necessary instruments, and we're also at studying collisions at the highest energies in the world. So no other facility could go to this high of energies for us to be sensitive for, let's say, as interesting of prospects. So in that sense, and because we have all of the necessary machinery to study these types of events, the LHC really is the best possible scenario.
Awesome. So if one imagines sort of beyond the LHC, would you be sort of like trying to push to higher energies? Like what might be sort of like future next generation improvements here?
Yeah, so any higher energy, even by a little bit, would be great. So even if the LHC ramps up to 14 TeV instead of 13, that would be helpful. But also, we would need these, we need to have these forward sets of detectors. And so there's plans to keep these around for the years to come at the LHC, which is great. But let's say if there was another accelerator built that didn't have these detectors, then we wouldn't be able to do the analysis in this way.
Wonderful. Thank you so much, Justin.
Yeah, thank you.
All right, are there any other questions or comments? All right, if not, let's thank again Justin for a very nice talk and for opening the Colloquium series, basically. I think it was very exciting. It's very, very interesting. So thank you very much to everyone for joining and for the questions and for and Justin for his talk again. Thanks a lot. And I guess with that, we close the first Colloquium series for graduate students. Thanks a lot.
Yeah, thank you so much, everyone.
What a start. That's going to be a tough one to beat.